I can begin. So one of the principles that lies at the heart of what I'm trying to convey in this class. But it's a principle that cuts across many spheres of computer science need. Even if you were to never take this class, even if you were to put aside this class, it's an absolutely essential thing that well-educated students need before graduating. I would argue in virtually any discipline is a sense of how things work at a mechanical level. It's a sense of explaining phenomena in the world in terms of why they come about, using a set of systematic explanations as to what are sometimes called mechanistic pathways, step-by-step explanation. In this class, we further aspire to a systems view, which reminds us that there's many lines to effect. There are feedbacks, reciprocal relationships that shape this. It's not just A influences B, B influences C, but sometimes A influences B, B influences C, and C influences A, right? But what's most fundamental here, in my view, is being able to explain phenomena systematically about why they're coming about in terms of specific causal effects, specific influences along the way. Now, this sounds modest. This sounds inherent in any technical education. But I'm no spring chicken, in case you haven't noticed. And over the course of my career, I have been distressed to find that many students somehow make their way through our program, and certainly through other programs at this university and others, without that sense. And when they encounter data from the world, when they encounter information from the world, their minds do not move in terms of understanding how it comes about, what gave rise to it, what was the generating process that led to it. And if you do not have that sort of hypothesis as to what gave rise to it, if you don't have some sense of as it would be called by my statistics colleague, the data generating process, you are doomed to carry around blinders in a very, very constricted understanding of the world. You are doomed to be at the mercy of arbitrary interpretations of things without being able to assess them, to evaluate them, to judge them, to critically assess them. I'm struck in the health sphere by the number of people lacking this sort of training. I'm not talking about physicians. No. Physicians do have a sense of this. This is why they got a medical school. But there's others who encounter data as if it's sprung from out of nowhere with no obvious relationship to other data. And they're not thinking mechanistically. They're saying, well, it's going up, well, it's going down. They're describing the data and not understanding the data. And if you think this is not, a concern, whether or not you master this for computer science, you are so sorely mistaken. I can assure you that when it comes to understanding computer problems, when it comes to explaining error messages that you encounter, when it comes to working through compiler complaints, when it comes to debugging user trouble incidents, when it comes to explaining unexpected crashes, when it comes to tracking down Heisenbugs where you try to pursue it and the problem seems to disappear. You need this sort of thinking. You need to be wondering, at what level the problem is occurring. Is it at the level of the network stack? Is it at the level of the server response? Is it something on the front end? You need to be able to explain observations from the world in terms of hypotheses about what might be causing it. It has long been noted in the software sphere that software engineers differ by an order of magnitude, that's 10 times, in terms of their ability to zero in on the cause of problems, to debug software. And a lot of it comes down, I've discovered, to a ability to formulate hypotheses for why we might be seeing certain behavior that operate mechanisms. Okay, this might be going on, it might be causing that. You might not know, you might not have confidence about the whole story, you rarely do, but you have some hypothesis for, okay, the problem might be occurring at this level, maybe this is happening, and you need to investigate it. What I found is that there are a distressing number of people in computer science, but yes, in health, who just observe something and they can describe it, but they have no idea where it's coming from. And at best, they flail against it because they don't understand where it's coming from, what's giving rise to it. And I speak to you as someone who, since the early 90s, has been fascinated not only by system science, but also the prospect of what became known 3 decades later as data science. Took my first first AI course in '88. My first course on neural networks and connective components in 1990. My first course in pattern recognition and machine intelligence, what became known as machine learning, in a more classic sense in 91, 92. And all those convinced me of the value of rich understanding from data in the world. But what I realized over time was that if you're equipped with some sort of understanding mechanistically about how processes operate in the world, if you bring to it a system science orientation, you can make use of that data in very, very rich ways. You can interpret it, you can relate it to each other. You can explain patterns, or you can posit hypotheses explaining patterns in it. It gives you a grounding, a footing for making sense of what is otherwise a cacophony of numbers. But if you lack that, mechanistic orientation, if you lack that ability to formulate hypotheses and reason about why things are occurring, you are doomed to take each number in those cacophony of data series simply on its own, isolated, fragmented, and you end up not being able to derive much value from that data. You simply say, well, cases are going up. Well, yeah, cases are going up. But are cases going up because it's the infection spreading, or are cases going up because you're more effective at finding those cases? They were already there, but now you go out and find them more easily. Those are two very different explanations. The first of them is bad. Infection is spreading more widely. The second of them is good. We're finding the cases before they spread. And eventually it portends that it will probably be coming down. But if you don't have this mechanistic understanding, at least articulated at the level of something like causal loop diagrams, you're going to be just unable to make sense of this cacophony. And one of my fears as a data scientist, as a systems data scientist, is that when it comes to application of AI and machine learning, if it's not coupled with some exposure to mechanistic thinking and system science, if it consists of shoveling into machine learning algorithms, no matter how sophisticated, could be transformer-based deep learning methods, could be, earlier generation of long short-term memory cells and recurrent neural networks, or it could be, ARIMA models or what have you. If you don't have a mechanistic sense about why things are occurring, and you simply pass the data in to get an answer, you're leaving money on the table. You're failing to secure the profound insights that data is waiting to happen. But it is waiting to give you those insights because you understand something. You're advancing theory about why this data is being produced. You're advancing some understanding of how one piece of data relates to another. One piece of data over time relates to the next. One piece of data about cases relates to pieces of data about hospitalization or data about deaths or whatever. It's those linkages that are the subject of our modeling. And whether it is causal loop diagrams at a high level, thinking through possible linkages step by step within the system, or whether it's in our simulation models, if we fail to bring this sort of mechanism-informed view, and I would argue a systems view with it, is very, very valuable, we are dooming ourselves to be drowning in a cacophony of data and ever more captive to machines that we just, to machine learning models we feed it into, and it spits out an answer that we can't fully evaluate. We are leaving off the table the most valuable things that we can come away, which is really an insight about what is this data telling us? What is it explaining? What is it hinting at? What is it suggesting? And to do that, you need structures that relate pieces of data to each other, pieces of data to what's likely to play out over time. And that's exactly what models give us, right? A simulation model tells us how our state now leads to state in the future, right? How our state now leads to a little bit of change that will dictate our state in the future. That's true for system dynamics. Our state now in system dynamics is summarized by the what in the stock flow model. It's summarized by the what, the stocks in the system dynamics model, and the little bit of change that's caused. The little bit of change that results from the stocks is in the form of the what? What captures change in system dynamic stock flow models? Flow. In an HMA model, the state may be captured in, for example, a state chart, and the little bit of change that results from that state over time might be captured through the what of that state chart? Begins with T. Transition. In a discrete event model, the state of the system might be summarized in people and different queues within the system and the current availability of resources. And what happens over the next little bit is dictated by, the amount of time that you spend once you have that resource within a given operator block until you can move on to the next one. Or it might be until the next resource is available. So all three of these methods involve state and some change over time. That dictates how the state now relates to the state in the short time in the future. Those models also knit together in an integrative way data about one part of the system with data on another part of the system. So if we were to go open up, and I would like you to do that for those with computers, it won't be absolutely required, but from the course site, the multi-clinic SIS hybrid saturation effects and lock-in, it's on the course site. This is a model which links together within a single model aspects of a person's state, aspects of clinic operation, the spread within a general population and to homes, right? This is a model that brings together these elements. If we add an SEIRS model, it would relate how things going on with susceptibles, like them getting infected, might relate to what's going on with infectives and to recovereds. So the point is that data about different parts of a system is not data about solitude. It's not just disconnected, fragmented, arbitrary in how it patterns. So we just describe it and say, who knows how it will evolve. It's something that's there to teach us, and models help us hypothesize how the system that gives rise to that data might work, how one thing might lead to another. And without that orientation, without that framework, we are failing to capture a lot of the insight that data is seeking to offer us. And in today's world, where we're increasingly surrounded by rich data sources from social media, from wearable devices, from smartphones, from weather sensors and environmental sensors of different sorts, from electronic markets, etc. In that world, that data can offer us a great deal of need if we know how to listen to it. And models provide the worst way of listening, except for everything else I know. They help us relate those different types of data to each other and the situation now to the situation in the future. They're not perfect, but as Winston Churchill said about democracy, it's the worst of all forms of government, except for everything else. And so it is with models. So in today's age of data science, in my view, it is absolutely essential that we do not simply take data as a bunch of numbers, take different time series, different piece of data about different parts of a system as just arbitrary, tabular data sets that we stuff into machine learning models and expect some outcome. The insights there are ripe for the plucking if you know how to relate that data to each other, if you know about those relationships. And that's what the craft of system science is in large part about. Also have to see what okay, so I'm going to cease my rant because we have some other material.